Welcome and thanks for joining us. I'm Linda Bell, Editorial Director at SAE Media Group, and I'll be your moderator for today's webcast, Thermostatic Control Valves, When Precise Thermal Management Matters Most, sponsored by ThermOmegaTech. Today's webcast will last about 30 minutes, and there will be a question and answer period at the end of the presentation. You can submit a question anytime by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible following the presentation, and those questions not answered during the live event will be addressed following the webinar. In order to view the presentation properly, please disable any pop-up blockers you might have on your browser. Let's meet our speaker. Glenn Quinty has been part of the ThermOmegaTech team for 18 years and is currently the Senior Design Engineer developing innovative thermostatic solutions for the aerospace and defense, industrial, railroad, and commercial plumbing industries. With expertise in complex design mechanisms and new product development, Glenn oversees projects from start to finish using DFM and DFA techniques to design thermostatic self-operating valves and devices. Now I'd like to hand the program over to Glenn Quinty. Glenn?
Hello, everyone. Thank you for attending today's webinar. Linda had already give you a little synopsis about me. I can pretty much skip most of that, but I guess with the main focus being on the last 18 plus years that I've been at ThermOmegaTech, most of my study has been here on developing and designing custom self-operating thermostatic valves for industries, as Linda had mentioned, ranging from the railroad, the oil and gas, and the aerospace and defense industries. So with that, let's move down to what is a thermostatic valve. So it's a device that automatically responds to temperature changes and self-adjusts to achieve and or maintain a desired temperature for a process or equipment. You see the two valves on the left-hand side. Those are basically two-way valves in that they have one inlet and one outlet. And they're used to, in this particular application, to maybe keep like a certain enclosure at a certain temperature or to keep a certain line within a certain temperature. On the opposite side, the right-hand side, you'll see two other two-way inline valves that are used on the other end of the temperature spectrum for freeze protection. So when the temperature drops down to around 35 F or so, the valve will open up, allow warmer, fresh supply water to come in, and it would close back off at 40 degrees, and would just sit back, and it would sit and modulate back and forth between 35 and 40 degrees. The main focus for today is the one in the center, which is what we call our M/D, or mixing and diverting valve, which is actually, as you can see, has 3 ports. It's a three-way valve, which makes it a little more of an active versus passive type of valve. So, you look at the valves I just showed. What's the main operating component inside is the thermal actuator, and as the bullet point says there, it's the heart of it all, and that is definitely the truth. It's a controlling element within the system. It senses ambient or fluid temperatures to convert thermal energy into mechanical motion. The invention was thought up in the 1930s. The wax-filled element was first used in automotive engine cooling. It is now used in a variety of applications such as heating systems, plumbing systems, industrial equipment and systems, and aerospace and defense. And right now we currently work within a range of 35 F to 250 degrees F. And as you see on the picture on the right there, there's a plethora of different sizes of actuators. One thing I just want to point and make note of is that the biggest one, second from the left, actually has a weight of less than a pound, is about 7/8 in diameter and maybe 2 inches long, but can lift a load of about 150 pounds, about 3/8 of an inch. And that'll become important a little bit later on. So now you see what the external of the actuator looks like. Here's how they actually operate. This is a phase change technology. So it utilizes a proprietary blend of paraffin wax that changes in volume as it responds to temperature, changing from a solid to a liquid and then back from a liquid to a solid. Various waxes can be used to phase change within a specific temperature range to meet application requirements, simply by just changing the wax composition that you're using. So as you can see on the right on the illustration, in the cold position, the wax is in the blue, of course, held back by a diaphragm. It's in its retracted state. So once it gets, once the temperature is raised to within the active region of that wax, the wax starts to change from a solid into a liquid, and when it's fully liquid, it will extend out, depending on the actuator, from a typical stroke range, as you can see there, of 0.1 inch to 0.5 inches. So from that motion that you saw right there, just diving just a little bit deeper into the actuator technology. And again, I hope this doesn't confuse anybody. I'll try and keep it as brief and non-technical as possible. Starting at the bottom left-hand side where the 0 and around the 150 is, if you follow the lower curve moving towards the right, so this would be so the temperature is rising now and the position is starting to lift off from that previous slide that I just showed, from its fully retracted point at 150, we'll say at the 0 point. If you follow this bottom line, the bottom curve, you'll see where it's the very first point you hit at about a 45-degree angle there is the point of inflection, and that's where it's starting to change from a solid into a liquid. And as you see, then the angle starts to sharpen more towards the vertical direction until you get to the upper point up at around 210 degrees, where you see what we call a knee. It kind of bends like a knee. And what that's indicating is it's exhausting its transition from a solid to a liquid, and now it's going back to just regular thermal linear expansion of all the parts that are inside the actuator, all the components. So now that's with it fully extended. Now if you look at it and now take that top line at 220 degrees and start reversing it back, you'll see you have that same type of knee, but it's a little bit behind, let's say at 207, 208 degrees, and you see where it says start phase change, liquid back to solid. So yes, so it's full liquid, now it's starting its transition phase, and as you notice, it pretty much mirrors the temperature up curve to the right of that, all the way down until you get right back down into the, down towards 165, 160. Now you're back into the thermal linear actually contraction of about 1,000th per degree F. And one thing to note here is on both ends of those spectrums, you'll see the thermal linear expansion and or contraction is about the same, about 1,000th per degree. So what we try and do is work with the meat of that stroke, so to speak. So the active range for this particular example will probably be between, I'd say, 200 and 210. That's where we get the bulk of the stroke range. You also notice there's a purple region, and that's designated the hysteresis deadband. And the reason that's there is because, as you can imagine, an actuator is usually lifting a load or force. So it takes more thermal energy to lift the load than it would to retract it, because as it's lifting it, the load is fighting the actuator. As it's retracting, the load is actually aiding the actuator in retracting, so it would take less thermal energy. That's why you have that little difference of a deadband. So for instance, if the actuator had stroked out, let's say all the way up to, on the lower curve, it strokes out, temperature rise to 210 degrees, and it stops at, we'll say, let's see, 2 tick marks down below 260. If you stop right there and start dropping the temperature, the actuator will not move. It's going to move horizontally across, and the actuator won't move until it drops to around, I'll say, 207 or so. Then from there, if you keep dropping the temperature, it'll follow that downward curve, the left side curve, just as shown. So hopefully I didn't confuse anybody about that. Again, we can help define it a little bit better in the Q&A section if need be. So the advantages of thermostatic valves. The main advantage is that they're self-powered, which means they can be located virtually anywhere. They don't require any electrical power, ideal for explosion-proof, spark-free environments. Used as a main source or backup failsafe for powered devices. Virtually maintenance-free, very predictable, very simplistic design. The actuator component has a high power to size weight ratio, or a low swap, and that's what I was talking about before. How that actuator being weighing less than a pound and being 7/8 in diameter by about 2 inches long can lift a 150-pound load no problem. Which having a low swap optimizing the valve performance, resulting in a compact size. So, taking a look at solenoid valves. So there are definite advantages to those, and the two most prominent are response time is in milliseconds, so there's no argument there, and also the exact temperature regulation can be done within tenths of a degree. But unfortunately, disadvantages are they rely on electric power, which if you lose power, now you're literally dead in the water. Requires multiple components to operate, as you can see from the example to the left. Leads to additional installation and maintenance expenses, increased space requirement, and potential disaster on power loss. And as you can see in the picture next to it there, so you have to have some type of power supply, some type of electronic control circuit, a thermocouple for feedback, and the actual solenoid valve. So the better option, well, that would be a thermostatic valve. Responds to temperature variations, utilizing a thermal actuator to either extend or retract a plug to control system flow. The advantages here are no additional components for valve control required, self-operating, lightweight, and a low swap. Reduces installation and operating costs. It's explosion-proof, requires no electrical power, which could cause sparking, and can be located virtually anywhere and in any orientation or position. And as you can see from the picture here, there's basically, there's mainly 4 components that go into this product, keeping it very simplistic. Now we're getting into the 3-way type valves. The one I previously just showed was one of our standard 2-way valves. So mixing and diverting valves, these valves are used to proportion flow in response to fluid temperature variations in both mixing and diverting applications. So in the left-hand picture, you'll see diverting mode. The flow comes up through the inlet on the bottom and goes to the left, which will be running right back to the sump. Once it gets to and above the target temperature, it then modulates, and the flow coming in will now go not from the left and now switches to the right, going through a heat exchanger. That same valve, believe it or not, can also be run backwards. In other words, you can have the hot coming in from the left side port, the cold media coming in from the right side port, and a mixed tempered outlet to whatever temperature you desire. So, and delving a little bit deeper, so into the mechanics of how these actually work, you'll see the cutaways here. So for the diverting, a single inlet flow of 1 of 2 outlet ports depending on the fluid temperature. So if you look at the bottom picture here, as most systems, at least the way I think of it rationally, most systems are going to start up dead cold. So it's starting up cold. You see the cold flow coming in, going through this lower port here. Now as the actuator heats up, it's going to extend out and it'll start modulating the spool, and so it'll lower the spool, choking off that cold port when it gets up to the target temperature, and now your flow has now been diverted to the upper port. It's still coming in the common right-hand side inlet port. If you flip the valve around and use it as a mixing valve for the center one, you see that it's going to modulate between the two. So you'll see on the lower picture, you'll have cold coming in and hot coming in, but at a much lower ratio. So knowing that the valve is too cold, what will happen is the actuator will move the spool, the internal spool, which ratio and proportions the flow of both the hot and the cold inlet to give you the desired balanced flow in the upper picture that you see there. And lastly would be the bypassing for 4-way manifold integrations. These are custom applications that we find on mobile vehicles. So it monitors the inlet flow and diverts fluid based on the temperature. So what you'll see here, this is a cartridge style that when it's cold, it will flow through there. Actually, some of it will flow a little bit through the heat exchanger on the upper picture there. But when it gets up to temperature, the cartridge style will close off that port and will have 100% of the flow go out through the heat exchanger or radiator and then back to the sump. A&D application examples: you have thermal bypass and hydraulic systems, avionic electronics cooling systems, fuel cell battery cooling loop, a gang nitrogen generation cart, fluid temperature control, and aircraft maintenance test stands. So here's your thermal bypass valve for hydraulic systems. I'll just read off here. Hydraulic systems need to maintain a specific temperature range for systems to operate efficiently. If it's too cold, increased fluid viscosity, high stress on the system components. If it's too hot, reduced viscosity, internal leakage, pump cavitation, and component failure can happen. So if you look at any typical VG120 hydraulic oil, which has a preferred operating temperature of about 105 F for best efficiency, starting in the middle, lower bottom there, where it says pump and motor. So when the system starts up cold, the pump's going to draw from the sump to its left up through the inlet of our diverting valve, and since it is cold, it's going to go right through the control valving and through the hydraulic cylinder loop and back to the sump. But because it's still cold, the viscosity is a little bit high. You're making the pump work a little bit too hard. So as that heats up, it's going to transition. Since it's VG125 hydraulic oil and its preferred operating temperature is 105, if you would put in a 95 degree A&D valve, what would happen is between 95 and 105 temperature that our valve will be sensing, it will then start to ratio and proportion between 95 and 105. By the time it gets to 105, you'll have 100% of the flow going to the heat exchanger and 0 going back to the valving system here. And it'll sit there and monitor that, and it will dither back and forth as needed, depending on how efficient or non-efficient the heat exchanger is. So again, what you're trying to do is keep and maintain that optimal temperature of 105 to help maximize the life of all the components within the hydraulic system. Next one up is avionics electronics cooling. So avionics cooling systems can rely on liquid-cooled cold plates to dissipate excessive heat. In these designs, coolant runs through the cold plate, removing heat and releasing it through the heat exchanger. The benefits are, for liquid cooling, eliminates temperature spikes. It's very compact, ideal for complex designs without space constraints and high thermal output. Also, lack of airflow for any of the cooling thin ones. And pump size can be optimized using thermostatic valves. So if you look at that, this is a closed loop circuit without a sump. So again, starting in the middle where the pump is, you'll see so the pump's going to initiate flow through the cold outlet manifold to each of the 4 cold plates in this example. And as the electronic circuitry that's mounted to it starts heating up, it will draw some of the heat away from it through the hot outlines, all those 4, to a receiving collector manifold, which would then go to the inlet of our diverting valve. And again, same thing as in the last example for the hydraulic systems. You'll see when it's below temperature, it'll just recirculate itself right back to the pump again. Once it gets up to the preferred operating temperature, it's then going to divert and send everything up through the heat exchanger to keep it at that temperature. And this last bullet point where it says pump size can be optimized using thermostatic valves, on the outlet line, on each cold plate where the hot out line is there, you can add what we call a reverse acting inline valve. And what that'll do is it will throttle it. If it's too cold coming out, it'll throttle it off. They'll let the other circuits that are too hot get most of the ethylene glycol or whatever media you have in there. So you can sort of optimize your pump if need be, and that would usually come into play when space constraints are very, very tight. For the fuel cell battery cooling loop, the fuel cell stack cooling system circulate coolant through fuel cell stacks where it removes heat to maintain optimal operating temperature. The A&D valve monitors coolant temperatures and directs it to either a heater or radiator to maintain temperatures within a specific range. The benefits are self-actuating, and it also eliminates temperature spikes. And as you can see here, the one different thing here is you actually have a heater added, and that's because when you have fuel cells, they have to be run at, there are certain optimum temperature ranges that they like to run at. And the example I like to use is the proton exchange membrane fuel cells, which run up around 90 degrees C. So that would be what this cooler is for. So upon startup, if everything's cold, our three-way mixing valve, it will go through the coolant will go through the coolant pump, and with it being cold, it'll run down through the heater there and go right back to the fuel cell, and continuing that loop until it gets up to around 85 degrees C. Then it'll start to modulate between the radiator and the coolant heater, and when it gets to 90 C, all flow will then stop going into the coolant heater and will be run through the radiator. And like I said, it will sit there and dither back and forth to try and ratio and proportion between the two to keep it at 90 degrees C, which is the optimum performance for the proton exchange membrane fuel cell. Next one up is the generic aircraft nitrogen generator cart, or GANG. The A&D valve controls the air temperature used during the air separation membrane process to optimize generation of high purity nitrogen. So GANGs are used for aircraft tire inflation, because you don't want any water in there because it would freeze up at altitude. Servicing of landing gear struts and pneumatic cylinders. Purging explosive gases generated by the use of emergency power equipment on some aircraft, and filling nitrogen cylinders. And our customer PCI was gracious enough to provide us with these photos. The one on the top shows the actual installation close up, that just piped in, and down below you see more of a bird's eye view of the whole system that it's used in. Fluid temperature control for aircraft maintenance test stands. The A&D valve controls the temperature of fluids in the test stands used for servicing aircraft. Benefits are self-operating and also eliminates manual labor. So if you have any type of hydraulic or pneumatic circuits that need to be run at temperature on the ground without the aircraft running to help simulate and make sure everything is still operating properly, that's exactly what the A&D valve would be used for. And again, that's where that second bullet point comes in, and how it eliminates manual labor in that it is self-acting and self-adjusting. Other A&D valve applications. Versatile technology allows a thermostatic three-way mixing valve to be used in a variety of applications, anywhere that precise temperature control is critical. And here's some examples over here. We looked at like electronic systems cooling, hydraulic fluid cooling systems, hydraulic thermal bypass, lube oil cooling control, lube oil thermal bypass, fuel oil cooler, cooling water control for radiator and heat exchangers, direct cooling with water, engine and compressor cooling systems, space vehicle cabin air control, loop type circulation systems, direct injection water systems, process control, makeup water, and mobile oil controllers. And if I could just back up, if I may, to the space vehicle cabin air control, the real big benefit there is people and anybody who's involved in aerospace, they usually want where energy and space is at a premium. This is probably the premier item to use for any type of temperature control, because it is self-operating and requires no additional external power source. Valve customization, that's what I've been doing for the past 18 years. Strict A&D project requirements, weight and space, again, coming in with low swap. Materials, we've worked with all these: stainless steel, aluminum, exotic metals such as titanium, Monel, Inconel, Hastelloy, you name it. Component traceability and serializations, custom temperature range requirements, and flow rates, the number of inlets, outlets, added features such as leak port, manual overrides, and even lock wires for aviation. And just wanted to thank everybody for attending. And you can see our contact info up here on the screen. And that's pretty much it.
Great. Thank you, Glenn. We'll now take some questions from our audience. The first question is, what is the accuracy of the temperature setting in the mixing valve?
So it's going to be whatever your normal setting is, plus or minus 8 degrees F. So what will happen in the mixing valve, like let's say for a 100-degree mixing valve, if it's set at 100, it would go down to 92, maybe up to 108. But what happens is it usually finds its own sweet spot during mixing. But if it's for diverting mode, it'd be the same thing, between like 92 and we'll say 108.
Okay. Let's see. Our next question is, what flow rates can each valve size accommodate? Okay,
so our smallest half-inch M&D has a CV of 2.7. So if you run the numbers there, and we always recommend a minimum of 1 psi delta across the valve to help it work accurately. So what you're looking at is maybe a flow of maybe one gallon a minute for the half-inch. For the 1-inch, there's a CV of 10.0, so that can handle a lot more. And we even have a larger 2-inch valve which has a CV of like 18, which can handle, I would think the minimum flow there would be probably 15, 16 gallons a minute, maximum probably up around 70 or 80.
Okay. Next question, what is the life of the valves? How many cycles can the wax take?
Well, we've had some that last up to upwards, I'd say 10 to 12 years, no problem. So I think the critical thing there is, depending on how active the valve has to work, that would depend on whatever the life would be of it. But the main advantage to this is, once it's plumbed into the system, the replacement cartridges are nothing more than just unscrewing a cap assembly and just replacing it with a new one, which literally takes 5 minutes.
What are flow and pressure limits of the hydraulic TBVs?
So far, up to, I believe, 300 psi is what we have now, although we have designed special applications up to 7,000 psi.
Is a thermostatic valve's response proportional or simply on-off? The person asking the question wants a valve that automatically opens more when the fluid temperature increases over a range of about 20 degrees C.
Yeah, see, so that's something that we would have to do a special blend of waxes for that. That last, or that slide where I showed that a regular typical actuator curve, that was on a single constituent wax. So in other words, a single temperature wax. What we would have to do is blend like 4 or 5 different temperature waxes together to help smooth out that or lessen the slope of that line to get it to work within a 20 degree C range.
Mm-hmm. How long does it take for the actuator to modulate fully from the open to closed positions and vice versa?
So depending on the size of the valve, I would say anywhere from 30 seconds. If you're taking it, shocking it from its fully, I'll say closed on one port side to the other, I would say probably 30 seconds, 15 to 30 seconds. But on our largest 2-inch unit, it might take upwards of 1 minute.
Mm-hmm. Let's see. We have time for one more question. How narrow a temperature range can be used?
Probably plus or minus 5, I would say. So certain valves, depending on the waxes that we have, and again, we would be bound by the type of wax that's used in that. There's certain anomalies in certain temperature waxes where it has to be at a plus or minus 8 degree range from nominal. But certain other waxes, like especially the lower temp waxes, it would be about a plus or minus 5 degree from nominal set point.
Great. Okay, thank you very much, Glenn. I'd like to thank our speaker, Glenn Quinty, for his presentation today, and all of our audience members for attending. You may download a PDF of the presentation slides by clicking on the Resources tab. Just a reminder that this webcast will be available on demand for 12 months at www.techbriefs.com. Thanks, and have a great day.
Okay, thanks, everybody. Thank you.